Hello, chemistry students. Today's lesson, or this lesson, we are looking at Standard 6A and 6B. We are introducing our acid, bases, and solutions concepts. Hopefully by the end of this lesson, you will have a refresher on some of the terminology, as well as an understanding of the major factors that affect how quickly substances can dissolve in other things. So, real quick review of some terminology that you might remember from physical science. When we are looking at a mixture of substances, it can be called a solution. A solution is specifically with one or more particles are distributed uniformly throughout another substance. These are homogeneous mixtures. The substance that is being distributed, that is being dissolved, is called the solute, and the substance doing the dissolving is the solvent. Our solute makes up the smaller amount of stuff in the solution. So whatever's in lesser quantity is technically the solute. So if you're looking at a liquid-liquid mixture, it's a little bit easier to identify. Now, when you're looking at a solid and liquid mixture or a gas and liquid mixture, your gas and your solids are typically your solutes. They are typically in lesser quantity. They are the thing that is being dissolved. The solvent is the substance that is doing the dissolving. It is in a greater quantity in the mixture. Some common examples. Non-chemistry examples, chocolate milk. So your milk is your solvent. It is the thing that's in greater quantity. The chocolate syrup is the thing that you put into the milk. It dissolves, disperses throughout it, and, turns our white milk brown. Kool-Aid, thinking about if you're making Kool-Aid or sweet tea, your water is your solvent, and your solute are the things that you put into the solution. Chemistry example would be an aqueous solution of sodium chloride, also known as salt water. So salt water solution, my salt, my NaCl, is the solute, and the solvent is the water. Water is known as our universal solvent. It is a substance that will dissolve a lot of other things. Now, since we're talking about some terminology, there are some types of solutions. So a concentrated solution is one where there is a large amount of solute. So we're dissolving a lot of stuff in the same amount of liquid, for example. Same terminology again. So thinking about a concentrated solution, in a concentrated solution of lemonade, we would have a lot of lemon juice and a lot of sugar. It would taste really, 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 really strong lemonade. Versus a dilute solution is where the solute is in small quantities. So, using my lemonade example again, I would just have maybe a little squirt of lemons and a little bit of sugar. It's going to have very little flavor to us in terms of how it tastes, and it's going to be dissolved in a lot more water. So your concentrated solutions tend to contain a large amount of solutes, and your dilute solutions contain fewer solutes. So if I were to compare two particular examples, both of these have 100 grams of water, and my amount of solvent, my water's my solvent, is the same. Notice the first example has 1 gram, the second example has 30 grams. So comparatively, the 1 gram solution would be considered the dilute, or the more diluted solution. The 30 grams would be a concentrated solution. So just some terminology. Concentrated and dilute are kind of relative. It just kind of depends on the substance that you're doing the dissolving. Some things you can dissolve a lot of the solid or the gas in the liquid, others not quite so much. So looking at specifically dissociation and solvation, these are some terminologies that's probably new to you as a chemistry student. So what is dissociation? Well, dissociation, just kind of a fancy way of saying dissolving. it's the process of breaking things down into smaller pieces. So when you dissolve a tablespoon of sugar into your tea, the water, the tea, is going to interact with the sugar molecules and kind of pulling apart into smaller and smaller pieces. Now, this can result in things that are charged, as in the example down below where bromine hydroxide is separated into bromine and hydroxide. Sorry, bromine. Anyhow, where it's separated into actual individual ions. Notice the charges. Or you can have things that are separated into neutral molecules. My sugar, for example, they're not going to form any kind of charged particles when it disassociates into the liquid. So disassociation is just the breakdown of larger pieces into smaller particles. So we can look at covalent things, ionic, non-ionic, doesn't really matter as long as it can actually dissolve in the substance that you are looking at. Oops, did not mean to do that. Now, this typically does not involve any changes of electrons, so there's no electron transition going on. It's just breaking it apart. So you know, I got a big old piece of substance, and we are slowly but surely cutting away and eating away little bitty pieces of it. Now, comparatively, solvation is the process where the solvent interacts with the solute. There are some attractions between these two particles due to our intermolecular forces. So those interactions is called solvation. My specific example here is sodium chloride, but a lot of ionic compounds do this, as well as many polar compounds can do this. So we're using water, our universal solvent, as the solvent in this example. And the solvation is what happens when each of those individual ions are surrounded by that water molecule. So there is attraction between each of the points of the solute, my salt, by the solvent. Now, it doesn't have to be individual ions. It could be actual molecules in the case of a polar molecule, such as an alcohol, for example. Now, this particular process involves the attractive forces that are present between hydrogen bonds. So the hydrogen bonding attraction, that is specifically, that is not what we're seeing here. That would be a good example would be probably your alcohol, because it's going to have lots of hydrogen bonds. Or attractions due to ion and dipoles. So water is very, very, very polar. It has a large dipole moment. It has these partial negative pieces, partial positive pieces. And there is attraction based on those partial charges to respective ions in many of our ionic solids. So the positive part of the water is going to go and attract to the negative ion, that would be the chlorine, and the negative part of the water is going to attract to the positive ion. That is solvation. Solvation is when the solvent molecules actually surround the solute, and there is some attractions formed due to our intermolecular forces. So you can have dissociation without solvation. You can have stuff that can dissolve into other substances but not actually have solvation. It requires a little bit of extra stuff in that molecule. It requires it either to be ionic or polar or have hydrogen bonding. So the second part of the standard that we were looking at is, oops, I got a little bit ahead of myself. Our big difference between dissociation and solvation is that dissociation involves the breakdown. So it's actually breaking big pieces down into smaller pieces. Where solvation is the interactions between the attractive forces in our substances. So one is breaking things down. The other is the attraction between the solvent and solute molecules. So looking at specifically standard, I believe it's, that is not the right number, whatever. So what are some of the factors that affect the rate or how fast something can dissolve into a solvent? So how fast can we make a solution? Well, it kind of depends on if my solute is a solid or a gas. There are different factors depending on what we are dissolving to make that solution. Now, there are three things that will affect how quickly a solid will dissolve in a liquid. So when you're looking at solids, the three major factors are agitation, temperature, and particle size. Those three things can affect how quickly it will dissolve. So agitation, that would be stirring, shaking, those types of things would increase how quickly the substance dissolve. It makes the particles, the solute particles, move faster, therefore it interacts with that solid more quickly and is able to actually break it apart and dissolve it into the solution. So, second factor, temperature. Damn it. Increasing the temperature will have a similar effect as of stirring or agitating. So if we increase the temperature of the solution, the solvent will dissolve more into the solute. So think about it. It's easier to dissolve sugar into hot tea than it is to cold tea. The reason that hot tea, the liquid is moving around faster, it's interacting with the solid sugar, and therefore it's able to dissolve it faster. The other thing that will actually make particles dissolve faster is by increasing the surface area. And the easiest way to increase the surface area is to have smaller particles. So if you have a large chunk of something that you're trying to dissolve, breaking it up into smaller pieces or crushing it up into a powder will make it dissolve faster. When you have like a cube, there is only a limited amount of surface area. Don't judge my drawing, but when you take that cube and you break it up into smaller pieces, now each side of that cube is now exposed even more to the liquid. So the total mass is the same, but the surface area increases. Therefore, we have more area for the solute to interact with the solvent and dissolve it. The solvent to the solvent, the liquid, to dissolve our solid. So easy way to remember this is just to think, crush it, heat it, stir it. Because if I do any of those three, I will increase the rate at which a solid can dissolve into a solution. So crush it, heat it, stir it is how we affect a solid. Now, for a gas, so if we're trying to dissolve a gas into a liquid, the factors are a little bit different. So with a gas, agitation, pressure, and temperature are a factor. So surface area is no longer a factor. Now pressure is a contributing factor. Now agitation, if you've ever shaken up a can of soda, you know how agitation affects how much gas can dissolve in that soda. You shake it up, all the gas is going to come out. And that's because you're causing the liquid molecules to interact with the gas more and push them to the surface. So agitating a solution that contains gases will actually decrease how quickly you can dissolve that gas. So you're not going to want to stir it or mix it. Temperature. For gases, you're actually going to want a lower temperature. Reason is kind of similar. So we want to decrease the temperature so that the particles hit the gas molecules less frequently. Because the more it hits the gas, the more likely it is to knock the gas to the surface and the gas will escape. So if you decrease the temperature of your liquid, of your solvent, you can dissolve more gas, your solute, into the solution. So colder mixtures will allow you to put more gas in it. It will retain the gas at a higher rate. And yeah. So pressure, how does pressure affect it? Well, we're talking about a gas. So if we increase the pressure of the gas, we're going to have more gas molecules hitting that liquid at the same rate. And if you've got more particles being forced into the liquid solvent, therefore it will dissolve faster. So higher pressures will increase the rate at which you can get a gas to dissolve. So increasing pressure. And I know I already said this, but not agitating it. So not stirring, not increasing the molecule's movement. So notice how for a gas, my two things that are similar, the agitation and the temperature, have an opposite effect. So for solids, we want it to be hot, we want it to be moving, we want to have very small particles. For a gas, we want it to be set still, we want lots of pressure, and we want it at cooler temperatures. So for the you-do portion of this particular lesson, there is a Google form. Once you get to the Google form, you're going to select the best answer for how the change will affect the rate of dissolving. That is it for this video lesson.